Non, c'est ça. Okay, so we'll start the talk. Thanks to everybody for being there. My name is Benoît Combemal from INRIA, and today I will present this talk together with Cédric Brun from OBO. So today we'll give a presentation about model animation, especially for debugging behavioral models. So what's a behavioral models? Behavioral models is models that represent a behavior. And while we are defining more and more domain-specific languages, we can find different kind of behavioral models according to the application domain in which we are using the behavioral model. So we can talk about business processes, about orchestrations, functional chain, activities, protocols, and so on. And in any case, the particularity with the structural model is that in a structural model, the model represents directly what we want to describe as the structure. In a behavioral model, the model element of the model are not directly representing the behavior, but describe the behaviors that can emerge by interpreting the model elements that are described into the model. So that makes it a little bit difficult to analyze a behavioral model because just by looking at the model, we cannot infer directly the behaviors that the model represents. We need to interpret the model according to the behavioral semantics of the language that we are using in order to emerge the behavior that is represented by the model. So that's a little bit tricky for early validation and verification of behavioral properties when we want to check some properties because we have to do a kind of mental processing in order to realize the interpretation of the model and see if the behavioral property is checked or not. So behavioral models can be used in many application domains, and we can do early validation and verification in many domains. That can be in software engineering or systems engineering, but that can be also in enterprise architecture or scientific modeling. Any application domain where we are using behavioral models and where we want to reason about the model early in the process. One technique, probably the simpler and the first technique in order to reason about behavioral model is model debugging, which is very similar to program debugging. So the main objective is to execute the model and to see the behavior which emerged by the execution of the model. So model debugging is basically traversing step forward the different states that the model will reach during the execution, and it corresponds to a very intuitive comprehension technique in order to just get a meaning from the model that we are defining. So there is no abstraction gap because we are not translating the model into another formalism in order to do the simulation. So we can directly animate, debug the models that we are defining, and there is a better turnaround due to this no gap in the abstraction level. So the main objective of model debugging is really to have a fast convergence towards an acceptable design in our models. An extension of model debugging is omniscient model debugging, which extends model debugging by the way to traverse forward and backward the execution trace. So while model debugging is only going forward and looking at the different states that a model reached during the execution, omniscient debugging also allows to go backward in order to analyze the previous states that we reached in the past. So the main objective is to be able to go forward and backward without replaying the execution, because of course we can always go back into the execution by restarting the execution at the beginning. So the main objective of omniscient debugging is to avoid this and to provide a way to replay a given execution similarly according to the different inputs that we had during the first execution. So we are able to go backward, and we are also able to replay in a similar way an already executed model. So that's an example of an omniscient debugging that we developed, a very preliminary prototype that we developed for activity diagrams. So what we can see here is an activity diagram, so which is the representation that we initially use for designing the models, for editing the model, and then we extend this representation for animating the model. So what we can see here, that there is a token here, so that's a fork node. When the execution arrives to the fork node, the token has been forked. So there is two tokens, this one which is there and this one which is at this point. So this activity is currently executed, and then probably in the next step, this one will be executed according to this token. We can also see the timelines that we produce. So here in this timeline, what we can see is the different states of the execution, and then we have a multi-dimensional trace that allows us to navigate through the trace according to different runtime data. So we can go through the different state of the model, but we can also navigate through the different state of a given runtime data if we want to just look at a particular information and when this information is changing. So that's exactly the same thing. So we start from a textual representation of the activity diagram, which is then represented graphically using Sirius, and here you can see the execution that I mentioned previously. Okay, so for getting this, what we need, so of course we need a graphical animator because that's what the user want to have when he debugs his model. And of course, in order to have this graphical representation, we need also to control the execution of the model. So we need a control panel. So the user is interacting with the execution engine using the control panel in order to execute the model step by step. And you can also define some breakpoints in order to execute until a breakpoint is reached, or having a timeline in order to navigate through the produced execution state. Of course, the link between these different tools and the animator is provided by the execution engine, and the main objective of the execution engine is to control the application of the interpreter in the model. And in case of omniscient model debugging, we also need a trace manager, which is in charge of saving the state of the model in the different state of the execution. So now the question is how to get this, and how to get this for free. So the main objective in our work with OBO was to provide generic tools for this one that are parameterized by the definition of the language that we use for defining the model. So the language is defined by a meta model, the model of the domain, which is defined in our case using eCore, and we define the graphical editor using Sirius. And the first thing that we have to do is to extend the definition of the editor by the graphical representation that we want into the animator. So we extend the representation of the editor by the graphical representation that we want during the execution. And we also extend the domain model by the definition of the execution semantics, so the computational steps that will involve the model during the execution. According to the execution semantics, we get the interpreter, which is parameterized by this, and which is able to apply the execution semantics into the model. And the graphical representation of the model animator is used by Sirius in order to provide the animator during the execution. The trace manager is provided by a generative approach. So we take in inputs the description, the definition of the language, and we produce a trace manager, which is as much as possible efficient. What I mean by efficient is that, of course, we are not saving the entire model for each state of the execution, but we try to save as much as possible resources, and in particular memory resources. And the control panel, breakpoint, and timeline are generic tools that are provided for and can be used for any kind of DSL. So as a wrap-up, Sirius animation that we introduced in this talk is based on the use of Xtend and Carmeta or directly Java in order to define the computational steps, the interpreter. And we use Sirius in order to extend the tooling that was defined for the editor in order to provide the animator. From this, we can use a generative approach for generating the trace manager. We can use a generic execution engine in order to link together the three first mentioned tools, and the generic control panel and timeline in order to control the execution and to navigate through the execution. So that was the introduction of the broader idea, and now we'll have a demo by Cedric about Arduino Designer.
Can you hear me? Okay. So Benoit kind of showed you the big picture, and with a small example based on activity diagrams. And at some point we were wondering, okay, but we'd like to have something to be able to test these technologies in one of the products we build and ship. And one of those products is Arduino Designer. So how many of you have heard about Arduino Designer already? So for all the others, it's basically a modeling environment based on EMF and Sirius, which allows you to define Arduino software based on the hardware you get. So you can define your board and how it's connected to some modules, and then you can define the software with a graphical and visual language. So it looked like a perfect fit for this kind of work where you want to execute something. Because one of the roadblocks you have when you want to see some execution on using Arduino Designer is at first you need an Arduino, and second you need to click one button which is going to generate the code, build it, and push it on the Arduino so that you can see your LEDs blinking. So as Benoit mentioned before, it's really, if you want to debug the Arduino code, you have some kind of reverse abstraction to do, which makes it harder to understand because you don't know how the code got generated from the model. And you also have bigger turnarounds because then you have to deploy the code and see how it goes physically and then go back on your program. So it's really a classic example of how you build tools with Sirius. It's basically an eco model which defines the hardware part of the software you're building and the program itself, which is a sketch. So just, I'm not going through the exact concept here, but what is interesting is you have the notion of steps of sketch which have instructions, and then in the instructions you can have if, while, repeats, basically the most basic programming language you can have, except we have a graphical syntax for it. Then from this model, we need to interpret it. And bringing it into Arduino Designer means developing two more plugins. The first one, being simulator here, is basically just Java code which is going to interpret the model. And this project, simulator.design, is the extension of the tooling so that the graphical modelers will update its shapes and actions depending on the current status of the simulation. So that's really two plugins which are keeping all the specifics of executing the models. In the end, with this experiment, it's like these two plugins are 14 Java files. So I mean, it's very, very small. In total, it's like not even 2,000 lines of code to bring the animation capabilities and simulations for this example. So that's really something you should be able to do quite easily. But again, here, the execution semantics is very easy. It's very small programming language. Everybody knows how to interpret it. In some other kind of languages with concurrency or parallel stuff, then it can be slightly harder. So it's made of two main Java classes. So we really took the most straightforward way to define this animator. Just one class which is actually extending the switch which is generated by EMF, which depending on the current instruction is going to do the work or simulate the work of the current instruction and maybe move to the next instruction. So this code is just basically updating the model states based on the current instructions so that we can move forward. and another class which is the execution engine, and the execution engine has the responsibility to control this execution and to say, hey, one more step, or stop, or start the simulation. So here we can see that when we're starting the simulation, we're actually launching a new thread and starting the Java code in another thread. And then from time to time, when the simulation gets stopped, we update the data by looking on the model, on the current instructions, and then getting back data into the debugging environment. So that's all good. We're able to execute the model, but then we want to see it being executed. And you're going to see it quite soon in the demo. So how do we extend the tooling? So Arduino Designer is defined with an eCore model and an ODesign file which specifies the graphical tooling. We define another ODesign file which brings some customizations. So we have a diagram extension for all the diagrams which are defined in Arduino Designer, which are adding a new layer here and adding new sections of tools. We'll see just later what those are, and updating and customizing the styles of the diagram definition. What is interesting here is that we don't have to change the actual tooling which we are shipping with Arduino Designer. We can just put more plugins which are going to customize it. So this customization is contributing actions. The actions are related to launching the debug from your graphical modelers, right-click, launch the debug, and setting breakpoints on some model elements. The styles, it's based on the style customization support, which is right into Sirius, with predicates like, hey, if the current object is simulating, then we are going to change the color of the label, the border, make the border slightly bigger, and in some cases update the path used to get the image of the current shape. So this all leverages the Sirius animation runtime, which first encapsulates step over step into return in EMF transactions, so that Sirius is able to see what has changed in between two steps. Bridge the Eclipse Debug APIs and the EMF API, so it basically sends events from the simulators back to the model and onto the Eclipse Debug support. And it also can initialize the tooling extension that I just showed before. So you can say, hey, I want to create an animator for this diagram definition. It's going to do basic choices like changing the color of the border in red and stuff like that. And more interestingly, it provides an off-the-shelf eCore model to keep runtime data. And this eCore model is actually pretty much a direct mapping with the Eclipse Debug API. So you can define a debug target which have threads and stack frames and current variables. This model is used by the execution engine to update. The execution engine will update this model data in between steps. And when it updates this model data, then Sirius will know that something has changed in the simulation and can update the view accordingly. It also brings support for launch configuration. Basically, you can just declare a launch configuration with Xtend, the one from the framework, and then get started. So this is a launch configuration for the Arduino simulator. But we're not going to see the launch configuration because in the case of Arduino Designer, we built a product which, well, kind of removed most of the Eclipse UI dedicated to developers. So we did integrate this slightly more nicely in the tooling. Here is Arduino Designer, as you may know it already. So we have the definition on the left, right there. So we have an Arduino board and a LED which is connected to the pin 13. Here is the program. So it's starting here. We are waiting for 300 milliseconds, lighting the LED, waiting for 300 milliseconds, putting off the LED and going back. So that's the Hello World example of Arduino Designer. So in Arduino Designer, which is, well, I only have big buttons and two perspectives. So we have the Arduino perspective to define the program. And then we have the simulator perspective, which is actually the debug UI you know in Eclipse. And I can launch the debug right there, and then we can see the LEDs blinking. So the LEDs are blinking because for Sirius knows that something has changed in the runtime model, which is kind of visible here. And we said, okay, if the LED is actually on, we're customizing the style, and this is the new pictures you have to use. So the pictures is changing each time to get the one with the LED blinking. What happens if we pause the execution? If we pause the execution, we can see in the program where we are regarding the instructions. And then using the classic shortcuts we have, we can go through the program and see the state of the system at the top. So these are the values of the pins of the systems. So that's the pin 13, which is the pin which is connected to the blue LED. And the value of this pin is, well, 1000 and so, and came back to 0, and came back to 1023, and so on. So we can inspect the state of the system step by step and see how the system evolves over time, considering the current instruction. Now I'll open another example, which is slightly more interesting. So that's a necklace example. It's basically, you have to figure out a cat with a LED necklace. So that's the part which is not simulated itself. So regarding the hardware, it's just a bit different. We have a push button, which is connected to the pin 0. And then we have 3 LEDs, which are connected. And what is the program? The program is going to check with an if that the button is pressed. And if the button is pressed, it's going to repeat 5 times the lighting on and lighting off of the LEDs. So what happens if I just start the simulation? So I'll start the simulation and nothing happened. I can see nothing on the hardware because actually I would deploy it on the Arduino and I would see nothing either. And that's because in my program I check for the push button state first, and the push button state first is just not set in some way. So if I do pause the execution, I can see that the execution is actually going forth and back in between the if instruction and checking the push button state, and never entering the if. But I can actually change the state and see how it goes. So the push button is connected to the pin 0. So I can just set the value of the pin 0 and then go back. And now we're entering the if condition. And now we can see that we are going through the steps of lighting the LED and putting it off. So I can go back and launch the execution again. If I'd like to inspect something, I can just toggle the breakpoints. So that's the action which is also contributed by this extension of Arduino Designer. And then the execution will pause, and I'm going to see all the values of the pins which are used, and well, so on. So we got virtual blinking LEDs. All these technologies have been developed in the context of the GEMOC project. So the GMAC project is first an Animator research project with many partners in France, many academics, and OBU and Thales. And it goes into a broader initiative which brings more people to the table, like people which are not in France and have no specific funding to work on these subjects, which is called the GMAC Initiative. So the GMAC project is focused on concurrent execution and simulation of heterogeneous models. So basically you have several DSLs which might have some concurrent execution semantic, and you want to see if, let's say, you have a deadlock or something like that. The GEMOC initiative overall is focused on what we call the globalization of models. So basically you have so many DSLs and you want everybody, all these DSLs to work together and keep consistency and analysis capabilities on this open world. So these are all the partners of the GMOC initiative. Basically, anybody which expressed interest and take part of the discussions and share their technologies. Speaking of which, so that's a research project. So basically, we have different levels of maturity within the project. So what we show you today is what we call ready for a pilot project. So we built the Animator and the execution engine, and we applied it on several use cases. So Arduino Designer is one of it. Activity diagram for the contest is another one. We also built FUML execution engine, which is integrated in UML Designer. Again, just to prove that the technology kind of works as expected. And now, we're in a phase of looking for some industrial partner which really needs, which would want to start a pilot project, bringing animation and these technologies into its own DSL-based tooling. But there are more technologies which are interesting in the GMOC project. So we have Mock-ML and Time-Square, which are focused on defining explicit concurrency in DSLs, which enables then all sort of analysis regarding concurrency, and be cool for coordinating patterns in between DSL, for instance. These projects don't have the maturity yet to get into a pilot project, but are still very interesting if you're starting another RD project and so on. So what about the Sirius Animator itself? So as I said, it's pretty cool. We have the technology, we applied it on a few examples, and we start to get feedback that, yeah, it might be interested in a few industrial use cases. So we have the technology, we want to share it, but on the other hand, it's not the same level of maturity that we have in Sirius. So we kind of created a Sirius Lab. And Sirius Lab is actually a collection of technologies which are generic, which means they fit in the scope of Sirius. And here, in the case of the Animator, it's generic in that it brings animation capabilities to any DSL, just like Sirius brings you the capabilities to define your tooling for any DSL, which have been proven useful, which basically means for OBO that we have been able to connect a few prototypes with it, and which we can, well, make it work, basically, and which are looking for an interest to bring it at a full maturity level. So it's mostly to raise awareness that these things are existing, and if you're looking for something like that, well, we can start from here. Oh, by the way, all these technologies are always EPL. So going back to the subject itself, what we've seen is the straightforward Peugeot Animator we did in Arduino Designer, which represents 2,000 of code. So it's only Java, but you have to code the interpreter, you have to code the execution engine, and possibly any additional tool you will need to control the execution in other ways, and so on. So it gets you very quick results because you don't have lots of stuff to do. But on the other hand, you don't have a lot of control on the execution. what we've seen before with Benoit is what we call an advanced animator, because as it relies on the trace manager, as it relies on the GMOC execution engine, you don't have to create your own execution engine. You just code the interpreter. In the case of Arduino Designer, you have to create the interpreter in a way which allows step-by-step execution. In the case of the advanced animator, it's handled by the execution engine. And in this case, it gives you more capabilities, like checking concurrency aspect, and more importantly, going back in the trace and maybe making some decision at some point and trying what if my push button is not pressed at this point, what happens next? So you can easily go back in history and go forward and get back again to the first state you were. So now to wrap up this talk, well, what you could do first is you can try the executable Arduino Designer. So we've been doing the extra mile on this one, and the extra mile is having a proper branch and build and something you can just download and launch on your own laptop. So it's all a package product, but it's tagged on the website of Arduino Designer with a 0.1 stream, because Arduino Designer itself is in the 1.something stream. We have many publications related to GMOC, so the whole problem itself about concurrency and heterogeneous DSLs. You can join the GMAC Initiative, which, as I said, is mostly expressing your intent of discussing with the other partners around the world. And you can get in touch with us being, well, OBO, for instance, to breathe life into your own designer. So let's say you have your DSL and you're interested in executing it, and we can move forward and start a pilot project or something and bring it at the level of being part of Sirius itself. Thank you for your attention. I think we still have a few minutes for questions, like 3 minutes. Do you have any question? Yes?
And the integration with the debugger, so how did you do that? Because you have the information basically of your runtime captured the model thing, and then you connect that one to the standard debugging framework.
Sorry, I didn't hear it.
You captured the runtime, basically, runtime information in DMF models.
Yes.
You link that one to the debugging.
Yes.
Facilities of that's basically it's part that would be generalized to easily create a debugging environment. You would like to do it that way.
Yes, exactly. So we capturing the information as we bring it to an EMF model, then the small framework we built is able to give the proper information to the Eclipse Debug APIs and detect when some variable has changed. For instance, during the demos, you see the variables are going yellow. At some point, it's because the value changed and so on. Which means by using an EMF model here, we can bring the awareness of the state into Sirius in a structured way, but we can also do all the heavy lifting of telling the Eclipse debugger about what have changed and what are the current variables and navigate to the model from the variable view, for instance. So it actually enables the reuse of this bridging without even thinking about it. It also takes care of navigating, right? So you click on the stack trace somewhere in the Eclipse Debug framework, just because in the EMF model you said, hey, this is the current instructions, or this is the context of the current execution. Then we are going to, well, open the diagrams if they are not open, and offering all these kind of basic and generic services. But it's always nice not to have to code them. Yes?
We saw animations of activity diagram. Do you animate sequence diagram?
No, we did not conduct any experiment on.
That's the next step, because we're currently experiencing this. So trying to implement the animator for second trigger, and
And by the way, there is another experiment which is going on, which is about bringing these capabilities into Capella. So I don't know if you've heard about Capella already, but well, it's focused on system engineering definition. And so there are a few parts which have behavioral definitions in the model. And a team in Thales is bringing these technologies and trying to apply it on the Capella use case also, which has some kind of sequence diagrams. That's why I mentioned that. Any other question? Yes?
Trace manager that you have, is there also a model on top of the trace manager? Is it also captured in the EMF-like model? Is there an abstraction to find the traces, etc.?
Yeah. What we are taking in input is the meta model of the DSL, and from this meta model we generate in the meta model trace meta model for this DSL. We're trying to be efficient.
Thank you very much. If you have any other questions, you can get to us during the breaks or during the sessions. Do not hesitate. Thank you.